Let's take a look at this example. This one is a little bit tricky one because we have extra resistors, okay, in series with the current sources. Please keep in mind that anytime you are going to solve the problem using the nodal analysis, you don't supposed to find the conductance or admittance of these resistors which are in series with the current sources. Okay, so we're going to find just the conductance of resistor R2, R3 and R4. Okay, so again I'm going to use letter Y to do so. So I have Y2, YY2 because I'm going to find the conductance of resistor R2. So Y2 is equal 1 over R2, which is equal 1 divided by 2 kilo ohms, okay, which is equal 500 microsiemens. Okay, next I'm supposed to find Y3. Y3 is equal 1 over R3, which is equal 1 divided by 1.5 kilo ohms. This is equal 1 divided by 1.5 exponent 3 is equal 667 microsiemens. Next I'm supposed to find Y4. Y4 is equal 1 over R4. This is equal 1 divided by 2.2 kilo ohms, which is equal 1 divided by 2.2 exponent 3 equals 454.54 microsiemens. Okay. Next, I'm supposed to find Y11. Okay, so I have, let me write this over here. Y11 is the sum of the admittances, okay, or conductances which are connected to node 1. So this is my node 1. Let me write this down. V1, and this is my V2, and this is my reference node, of course. So as we said, we do not consider this resistor. That's why I'm going to write that Y11 is equal Y2 plus Y3, where Y2 is equal 500 microsiemens plus Y3 667 microsiemens. Okay, this is equal 1.16 millisiemens. Okay. Next, I'm supposed to find the admittance between these two nodes, right? So this is my admittance Y3. So I have Y12 is equal Y21, and this is equal Y3. This is equal 667 microsiemens. Next, I'm supposed to find Y22. Okay, so this is the sum of the admittances connected to the node 2. So I have Y3 plus Y4. Keep in mind that anytime I say admittance, this is the same thing like conductance, okay? So we have Y3 is equal 667 microsiemens plus Y4 is 454.54 microsiemens. this is equal 667 exponent 6 negative plus 454.54 exponent 6 negative. This is equal 1.12 millisiemens. Okay, so next we're supposed to find the sum of the currents going to node 1. So I have sum of the currents going to node 1. So because this current I1 is going to the node, okay, 1, to the first node, I'm going to write that this is equal to I1 and this is equal 5 milliamps. Okay, if you are going to look at the node 2, some of the currents going to node 2 is equal simply negative I2. Negative I2. Why is negative? Because the current is leaving the node. So this is equal negative 9 milliamps. Okay. So now we are ready to write the general formula for the two-node circuit. Okay, so I have my nodal equations. Okay, so I have y11 v1 minus y12 v2 is equal sum of the currents going to the node 1. And I have negative y21 v1 plus y22 v2 is equal sum of the currents going to node 2. Okay, so this is the general formula for the two-node circuit. Okay, so now we are ready to substitute y's by the numbers. Okay, so I have y11 is equal 1.16 millisiemens. So I have 1.16 millisiemens v1 minus y12 is equal 667 microsiemens. So this is 667 microsiemens, and I have v2 is equal to the sum of the currents going to node 1. We found it. This is equal 5 milliamps. Next, look at the second equation. We're supposed to write negative sign, and I have y21 is equal 667 microsiemens v1 plus y22 is equal 1.12 millisiemens, and I have v2 is equal negative 9 milliamps. So I have two linear equations, and I'm supposed to solve them for v1 and v2. If you want to do this manually, you can do this manually using, for example, determinants, or you can do this by the calculator. Let me just give you a hint, and because some of you can have difficulties to remember this formula, I always write this formula like that. So I have y11. Anytime you see 1 1 or 2 2, so these y's are going to have always positive sign at the front. If you have different combination like 1 2 or 2 1, they are going to have always negative sign. Okay, so imagine this is like a first row and first column. Okay, first digit represents the row and the second digit represents the column. Okay, so this is my first row and first column. This is my first row and the second column. Okay, so this is the way how you're supposed to organize the formula. Maybe this is going to help you to remember this for longer time. So next I'm going to use the calculator. So I have my 1.16 exponent 3 negative, and I have negative 667 exponent 6 negative, and I have 5 milliamps, 5 exponent 3 negative, and I have 667 negative exponent 6 negative, and I have 1.12 exponent 3 negative, and I have negative 9 exponent 3 negative. Okay, so my V1 is equal negative 471.72 millivolts. Okay, so this is voltage at node V1, voltage between this point and ground. Next, my V2. V2 is equal negative 8.31 volts. So this is the voltage between this node and ground. Next, I'm supposed to find voltage VR3. VR3 is the voltage, okay, voltage across resistor R3. So this is nothing else, just the difference. This is the difference between these two voltages. Okay, so I have VR3 is equal V1 minus V2. This is equal negative 471.72 millivolts minus negative 8.31 volts. This is equal, I have negative 471.72 exponent 3 negative. Negative times negative will give me positive plus 8.31. This is equal 7.83 volts. Okay, so this is the voltage across resistor R3. Next, I'm supposed to find the current which goes through the resistor R3. So R3 is equal VR3 over R3, where VR3 is equal 7.83 volts divided by R3, which is equal 1.5 kiloohms. Okay, so this is equal 7.83 divided by 1.5 exponent 3. This is equal 5.22 milliamps. Next, I'm supposed to find the current at resistor R3. So PR3 is equal IR3 to the second power times R3. So my IR3 is equal 5.22 milliamps raised to the second power times R3, which is equal 1.5 kiloohms. Okay, again I'm going to use the calculator. So 5.22 exponent 3 negative to the second power times 1.5 exponent 3. This is equal 40.87 milliwatts. Okay, so this is the power at resistor R3. If you want to find the power at resistor R4, Okay, so keep in mind that the voltage across resistor R4 is equal to V2, okay, because V2 appears across this resistor. That's why I'm going to write that PR4 is equal V2 to the second power over R4. Okay, so this is equal, I have V2 equals negative 8.31 volts we found over R4, which is equal 2.2. Don't forget that we're supposed to add the power over here. So we have 8.31 negative to the second power divided by 2.2 exponent 3. This is equal 31.38 milliwatts. Okay, so at this moment we can say that the problem is solved.